Now, obviously, a pipe, you can write to it many times, and eventually when you close a pipe, then that sets the pipe to a particular state that says not only is there no more data available right now, but there will not be any more data in the future. So after writing 10 bytes total to the pipe, then we close the write end, and that means that as we loop over the read end, reading 3 bytes at a time, and we get the number of bytes available. So it's going to keep looping until eventually we get a 0 back, which is saying that not only nothing is available from the pipe, but nothing will be available, in other words, an end of file. And then we'll break out of that loop. So what we'll see is we'll see the first 3 characters written to the pipe, the second 3, the third 3, and then the last one will just get, n will be 1 for the last little bit on the D there. So we can try that out just to make sure. Right, so hello world printed as expected. If I leave this close out right here, then our program will print hello world without the D, and then it'll get stuck because it's waiting for 3 bytes. And only one of them is, well, it prints the D because that's immediately available. So getting a short read back doesn't mean that you hit an end of file, it just means only 1 byte was available right now. On the other hand, if 0 bytes are available, then read will wait on the pipe until more data is available, and more data is not going to be available in this case. When we mix pipes and fork, then this closing of the file descriptors becomes even more interesting. So here I am creating a pipe, fork, and writing on the child side, and then closing the file descriptor explicitly. And then the read side, we have that same sort of loop we have. Now I don't have a close, I've commented out a close on the parent side, but the child side does close it. So let's see what happens. When you run this pipe program, then we see an effect similar to where I didn't have a close before. So if I uncomment that close, then the pipe goes into a state where it knows no more data will become available, and the process will be able to finish after hello world. So again, what we saw there is that this program got stuck unless this close was here. And the reason, generally speaking, is because there are 2 processes and they both had a handle to the right end of the pipe, so either one could conceivably write to that pipe. And it's only when both of them explicitly close it that we know that there's an end of the pipe. Let's look at a picture that shows this. So the way a pipe or other files are set up is there is a file descriptor table. So there are some numbers. If we looked at the result from pipe, it turns out the numbers are 3 and 4. Let's look at that. So I've got 2 file descriptors here. I can print them out. FD is 0, FD is 1. Okay, so 3 and 4, it turns out, were the numbers that are representing those file descriptors, the ends of the pipe. What that means is that the operating system kernel is keeping track for our program, for our process that's running the program, that file descriptors 3 and 4 both refer to eventually a pipe. But 3 is the read end, and 4 is the write end. In other words, 3 corresponds to a read object, and 4 corresponds to a write object, where both of those objects share the underlying pipe data. Right? And maybe there's a position where they're keeping track of, and so on. So in this case where I just have a parent process and I close the write end, that means the number of references to this object goes to 0, and it can update the shared state to say that's the end of the pipe. No more data will become available. On the other hand, if I start out with the pipe and then I have a fork, that means I create another per process file descriptor table for the child process. Fork copies that whole table just like it copies everything else about the parent process, and that means that our read and write objects, which are shared across all processes, now have reference counts of 2 on them. And they have to have reference counts of 2 because they're shared by, well, And they have to be shared across all processes because that's the point of a pipe, to be able to communicate across processes. So that means the read and write objects are shared across processes, and the underlying data is also shared. So in that situation, when the child process closes the write end, then the reference count goes down to 1, but it's not down to 0. And that means there's still a possibility that data will be written to the underlying pipe. In fact, it doesn't matter whether the child process did that close, because when it exits, its references to both the read and the write objects will go away. Meanwhile, the parent process has to actually close the output file descriptor for the read side to know that no more data will be available.